Yeah. So basically, scope measures are going to give us the idea that how tough the controllability and observability of the VLSI circuit is. Scope measures is actually going to give us the sources of correlation error, combination circuit examples and sequential circuit examples we are going to cover, and how big the test length can be. So the prediction of the test vector length we will be finding out with the scope measure, and the high level testability measures we will be covering in this particular talk. So what is the purpose? There is a need of approximate measure so that we can find out what is the difficulty of setting the internal node to 0 or 1. Means we want to push the internal node line to 0 value or 1 value, but we have the control only on the primary inputs. For example, let's assume that this is a circuit and we have, let's say, we have a fault over here, right? So this fault actually is not visible. What is in control with us is these set of inputs. These are in our control. I can control this well. Controlling both of these inputs is very easy. I can make 1 or 0 as per my requirement to the inputs. And at the same time, if I'm talking about output Z, so this is difficult to control, because controlling this means these are the primary input sets. So controlling this, making it 0 or 1, it is in my control because inputs are in my control. So controlling the inputs is easiest possible. So effort to control the input lines is the easiest possible. Likewise, controlling the output is the toughest possible. We have to find out that what was the output if this set of inputs was available. So that is going to be difficult most, right? Likewise, if I'm increasing the level of the gates, for example, this line, let's say its name is H. So this H line is a little bit difficult as compared to the input sets, right? Controlling the H line is a little bit difficult as compared to the input sets. So it means the difficulty level is increasing from, let's say, these AB inputs to H and then to Z, which is the output. So controlling AB is the easiest one. Then controlling H is a little bit difficult. Controlling Z is the difficult most. So this is how the controlling of any net, any line, any branch in the circuit is having the difficulty level. Likewise, let us consider the observability. Observability means how you can observe that particular node. So observing the output, observing means looking into, right? So I can look into this output easily. I can visualize what is the output very easily. I can visualize because outputs are visible to the end user. So whether it is output is 1 or 0, I can visualize in a good way. But visualizing what was the input is again the difficult most. If the output is on or off, what was the input? It is again visualizing that is difficult most. So it means the controllability is having the difficulty level, let's say from 1 to infinity in this way. Likewise, observability, observing something is having the difficulty level in the reverse direction. Let's consider it from 0 to infinity in the reverse direction from output towards the input. So these difficulty, how difficult a circuit should have its internal nets or all the nets setting the values to 0 to 1, that is a measuring. There are different measuring algorithms in the literature, and this is the job of the testing measuring measurement algorithms. Okay, so why the internal nodes we need to put 0 or 1? For example, this fault H is stuck at 1. So if this is stuck at 1, what I need to put over here? My job is to make sure that this H is pushed to 0. So that I can have 0/1. That is nothing but D dash. Okay. So my job is to bring d dash over here. So here the goal is bringing h is equal to 0, and that is the intermediate node. So easily I cannot have it. So it means I have to figure out with the help of testability algorithms that how difficult it is to bring this h line to 0. That is known as the combinational controllability 0 at this particular h line, because it is a combinational circuit. So controllability for 0 is different, controllability for 1 is different, right? Controlling 0 is different. For example, we are talking about AND gate. So in AND gate, controlling 0 is easiest possible, right? Because we have 3 combinations. We will discuss that later. So basically, testability analysis involves the circuit topology analysis, but no test vectors and no search algorithms are there. So it is the static analysis. Linear computation complexity is there, otherwise it becomes pointless, because automatic test pattern can generate the exact fault coverage and the exact test vectors also. In the literature, there are few algorithms like T-measure algorithm, scope algorithm, test screen algorithm, Camelot algorithm, Covector, and Comet algorithm. So these are a few of the listed algorithms found in the literature. Out of these, the scope algorithm is one of the popular algorithm. We will only discuss the scope algorithm in this FDP. What is the scope? The meaning of the scope is the abbreviation of SENDIA, Controllability and Observability Analysis Program. This is the name of the investigator, and the other part is the controllability and observability analysis program. It is the expansion of the goal of this particular algorithm. So we will be using these things continuously while the controllability and observability analysis. So there is something called as CC0. It means it is how difficult setting circuit line to logic 0 in a combinational circuit or a sequential circuit, but we are assuming the combinational nature of it. Okay, so CC0 means combinational controllability. First C stands for combinational, next C stands for controllability, and next 0 means controlling that particular value to 0, that particular line to 0. So CC0 means you are going to control that particular line to 0. CC1 means you are going to control that particular line to 1. So that is CC1. Likewise, there is combinational observability. Observing, you are going to observe the output, right? For example, this is AND gate, so you are going to observe this output. This output you are going to look. Can you fix that this output that okay, I just want to look 0 or I just want to look 1? No, whatever is available, you are just observing that. So observability is not having observability 0 and observability 1, because whatever is available, that only you are going to observe. If 0 is available, you are going to observe 0. If 1 is available, you are going to observe 1. Okay, that's what the combinational observability is represented by CO only. Likewise, for sequential measures also analogously, we will be having SC0. S stands for sequential. The first S stands for sequential, and then this C stands for controllability, and then 0. So sequential controllability is used for sequential circuits. So SC0 stands for sequential controllability 0. SC1 stands for sequential controllability 1. And likewise, SO stands for sequential observability. So you are going to observe any of the branch in the sequential circuit. So that is the SO. We will give these some number, because we just want to figure out how difficult as compared to the input or output line the controllability or observability respectively is. So we are going to give this. Gaurav, am I audible well?
Yes, ma'am, you are.
Okay, thank you. So, dear audience, if there is any question, please keep on typing in the chat box. We'll take the questions after a while. Okay. So range of scope measures. What is the range of scope measures? Since we just want to figure out how difficult it is. So finding a difficulty instead of having some tags, okay, easy level, hard level, difficult most level. Instead of that, if we have a number, then the relation between the easiest most and the difficult most is easy to correlate, right? So because of that, the scope measures are taken into numbers. So in some books, controllabilities are going to start from 0 to infinity, and observabilities are also going to start from 0 to infinity. And in other books, controllability may be easiest, they are taking the scale 1 to infinity, and observability also 1 to infinity. In this particular case, it's been taken controllability starting from 1 to infinity, observability from 0 to infinity. These are the range of the scope measures have been taken. So 1 or 0 means it is the easiest most, controllability and observability respectively. Infinity means it is the hardest most. Okay. So combinational measures, roughly these will be proportional to the circuit lines that must be sent to control or observe the given line. This is the rough rule for the combinational measures, while in sequential measures, there is a twist. Sequential means there is a circuit and then we have some feedbacks, right? So in one go, if we are not able to fix all these, our job is to bring these infinities to some number. So in first go, if we are not able to bring replace this infinity to a particular number, it means we have to repeat the process again and again. So it means this will be decided by roughly the times of flip-flop must be clocked to the control or observe the given line. That is going to decide the sequential measures. So Goldstein's scope measures are represented by this way: AND gate output zero controllability. What does it mean? There is an AND gate. So how I can control its output to be, this is output controllability 0. So let's give some name A, B and C. So my objective is to bring 0 over here. How many input combinations I can have? So I can have 0, 0, 0, 1 and 1, 0. There are 3 combinations. Can I roughly say that if any one of the inputs is A or B is 0, then I can have C is equal to 0. Just type Y in the chat box if you do agree. If any of the inputs is 0, it means I will have output is equal to 0. Yes or no? Yes, please speak up if you do agree with this. So it means what? Yeah, thank you so much, Devasis. So it means what? I have to put my CC0 combinational controllability 0 at C branch is given by minimum of what is my job? Either A or B is expected to be 0. That means the easiest possible way I can bring A or B to 0 plus 1. Plus 1 is for any combinational circuit. If any combinational logic gate, if you are crossing, it means you have to add 1. Please remember, whenever you are crossing any combinational logic, you have to make plus 1. If you are increasing sequential circuit, then the sequential controllability and observabilities will be plus 1. So these are the levels. Okay. So logical gates are combination logic. So we will be doing plus 1 in the combinational controllabilities and observabilities. If we are talking about sequential circuits like flip-flops and all, we are crossing those in forward or backward. In that case, we will make plus 1 in the sequential controllability and observability alone. So here minimum of CC0 of A or B. A comma CC0 B. because any one, either A or B, I should have 0. So it means minimum of. Easiest way with the help of which I can get 0 at A or B. Plus 1 because I have changed the label. So CC0 of A, CC0 of B plus 1. This is what I have to do. So this is what the CC0 I will be having. Now let us consider the CC1 for AND gate. So CC1, when I can have the output 1. So it means the only combination when inputs are 1, 1, I can have the output 1. So how I can represent this? For sure, A is expected to be 1 and B is also expected to be 1. If there were multiple inputs, then all of those are expected to be 1. It means I have to make sure A is 1, B is 1, C is 1 and like that. So it means CC1 just a minute. So CC1 of C can be written as summation of, because for sure all of the inputs are expected to be 1. So CC1 of all inputs. So I am representing all inputs by A. CC1 A plus CC1 B plus CC1 C plus like that and plus 1. So that's why this is the formula for input controllability. Sum of all the input controllabilities at CC1. You have to write it CC1. And this is the minimum controllability CC0. And likewise for out or XOR gate if you want. So for XOR gate, how you can have it? So first of all, you have to bring the truth table, right? So output controllability will be minimum controllabilities at the each of the gate input set. How you can determine that? For example, you want to have for XOR gate, you want to have output controllability with, let's say you are having the XOR gate. I'm just taking one example. This is A, this is B, and this is C. So with the truth table, I can have these two combinations when I can have the output 1. So if I want the controllability CC1 at C, what it should have? It should have for sure A is equal to 0 plus B is equal to 1, comma, A is equal to 1 plus B is equal to 0. So minimum of these two. So my formula becomes minimum of CC0 of A plus CC1 of B, comma, CC1 of A plus CC0 of B, and plus 1 because one level is changed. So here we have to note one thing, that this XOR gate is considered to be one entity only. XOR gate can be made up of multiple gates. In that case, those gates will be considered separately, right? But in this case, XOR gate is one entity, so we will just take plus 1. If there were multiple gates, let's say XOR gate was prepared using the basic gates, so the levels will get changed. In this particular level, there is only one level, so just plus 1. If we are using basic gates, then AND gate, OR gate, NOT gate, there will be multiple levels. 3 levels will be there. So at least plus 3 you will get at the end of that particular circuit. So that is the difference. Likewise, let's say XOR gate is made up of all NAND gates. So the levels will be different. And depending on that level, you will be getting the different controllability and different observability. Likewise, for fan out and stem observability, first let us have the fan out stem controllability, how you can control. So if this is the fan out branch and you have some CC0 or CC1 over here, so it means it is controlling this also and this also. It means it will become the same. Controllability will remain the same as we have also discussed in the equivalence and dominance based collapsing, that whatever input you have, the fault is there, that fault is going to propagate in all the all the branches or the fan out. So likewise, CC0 and CC1 of the stem is being propagated to all the branches equally. But if we talk about observability, so observing, like looking back to this, means this observability, we will be taking the minimum possible. If I can visualize the input effect at a single output, then also I can say, okay, this was the observability. So observability, when we are talking in this way, so observability of the stem will be the minimum of possible of any of the fan out branch. That is the observability for the fan out circuit. So these are the basic controllability examples we have already discussed for AND gate. We can discuss for OR gate. So for OR gate, let's consider the CC0. In CC0, when I can have 0, for 0, I have to make sure that A and B are expected to be 0, 0. So it means sum of CC0 of A plus CC0 of B, and this plus 1 is because of the level change. If I just want to calculate CC1, then there are 3 combinations for CC1, 0, 1, 1, 0 and 1, 1. Can I say that the minimum possible, any one of the input, if it is 1, then I can have the output is equal to 1. So that's what we will be taking, minimum of CC1 of A, comma CC1 of B plus 1. And that's how this is going to give us the CC1 for the OR gate. XOR gate we have discussed. Let us discuss for the NAND gate. So for NAND gate, whatever we have for the AND gate, it will be just reverse of that. CC0 is replaced by CC1 and CC1 is replaced by CC0. The reason being, when I can have CC0, I will have CC0 when both of the inputs are 1, 1. Okay, and this combination was giving CC1 for the AND gate. So it means these are interchanged. This is changed with this, and this one is changed with 0 of AND gate. Likewise, for XOR gate and XNOR gate also it will remain same. For OR gate and NOR gate, it will remain same. Okay, for NOR gate, you can see if there was a NOR gate, and this was CC1 of it, and this was CC0. This will get converted to CC0. For XOR gate, it is, it is worthy to understand. For XOR gate, both of the things, I can revise it again. CC0. 0 means when I can have 0. So there are 2 combinations. I can have CC0 for OR gate if I have 0, 0 or 1, 1. So it means either I can have this combination or I can have this combination. For this combination, A is expected to be 0 plus B is expected to be 0. So CC0 of A plus CC0 of B, comma, other combination is 1, 1. So CC1 of A plus CC1 of B, and this 1 is because of the level change. So that's what, because there are 2 possibilities, so that's what I have to choose the minimum possible, right? So minimum possible CC0 of A plus CC0 of B, comma CC1 of A plus CC1 of B I can take, and that's going to give me the CC0. And likewise CC1, because CC1 gives us the combination like this is 1, 0 and this is 0, 1, and that is responsible for getting 1 at the output. So that's what we can have it in this way. And for XNOR gate, it will be just reverse of that. Why it will be reverse of that? Because for XNOR gate, I just need to put one bubble over here that is going to make this 0 at the output to 1 and this 1 at the output to 0. So both of these will get interchanged for the XOR gate. So I request all of you to please keep the paper and pen handy so that along with me, you can just note down that how the things are going on, so that when we will be solving a little bit complex circuit, then it will be easy for you to understand and do it along with me. So these are for XNOR gate, NOR gate and others. For inverter, let us understand. Inverter is a logic circuit, so one is for the level change. How I can have CC0 at Z? So for that, I have to make sure that A was expected to be 1. So that's what this is, CC1 at A plus 1. Okay. Another one, when I can have 1 at the outputs, only one possibility that input is expected to be CC0, A plus 1 because of the level change. So yeah, what about buffer? Anybody can help me to find out the CC0 for buffer? Buffer is a circuit. Let's say it is somewhat like this. Or let's say I'm connecting two inverters back to back. Now you may tell. So let's say A is the input and Z is the output. So what is the CC0? CC0 of Z can be what? So CC0 of Z can be CC0 of A plus 2. You understand this or not? CC0 of A plus 2. In this particular, it is A plus 2. In the previous case, when the buffer was the single entity, it was CC0 of A plus 1. Why? Because here I have two levels. There are two levels. So if I'm considering that this is X branch, so first of all, I'll get for CC1 for X. So I'll be getting CC1 for X is this. Then again, I will apply the formula CC0 for Z is equal to CC0 for X branch. Means this much I will be having plus one more one. So definitely I will be having CC0 of A plus 2 for buffer. So likewise, controllability we have gone through. Likewise, we will go for observability. So observability means how I can observe. So how I can observe that I will take into consideration in terms of controllability, because controlling the inputs is in my hand. Now, how hard is to control, that is going to decide how hard it can be to observe. Okay. So observing over here is going to give me the easiest level. That is, we can have it 0. Let's say observing over here is having the 0 offer. Now observing the input towards this side is actually difficult. So now let's say I am just observing this, and now I want to find out the observability of CO of A branch. So finding the observability of A branch, what I have to do? First of all, I have to make sure that the other branches, all other branches are non-controlling. So what is the non-controlling value for AND gate? Please type in the chat box non-controlling value for the AND gate. Yes, can you type in the chat box non-controlling value for the AND gate? Yeah, very good. So non-controlling value for AND gate is 1. So it means if I'm having this B is equal to 1, it means whatever I will be having at A, I can observe that at the output, right? Yes or no? Yes, correct. So what I'm going to do is, if I want to find out the controllability of any of the input of AND gate, I will make sure that all other inputs, if there are multiple inputs, all of them will be set to the non-controlling value. Non-controlling value is 1. And because of that, CC1 of B, putting that value to 1 is what? Controlling that value to 1 is CC1. CC1 of B plus 1, because there is a level change from output to input you are going to come. So this is CC1B plus 1 plus CU of Z. It was having some observability offered at output, and that has to be added with this particular and plus 1 because of the level change. And likewise for CO of B, I will be having, I have to fix the non-controlling value at A and plus CO of Z, because already that hardness level is available, and plus 1 because of the level change. Now, if let's say I have a 3-bit 3 input AND gate, can we calculate the control observability of one of the input for that AND gate? So let's say here there is the third input. This is the third input C. So in order to observe this A, what I need to put this A is equal to 1 and C also equal to 1. So what does it mean? I will be observing this after this at the output. So it means whatever difficulty level was here, that is existing. difficulty level of setting B is equal to 1, that is CC1, controlling the value of B to 1, plus CC1 of C and plus 1 because of the level change. So this is how we can calculate the input observabilities for the all the inputs for the AND gate. Likewise, let us come for the OR gate. So the formula will remain simple. You have to figure out the non-controlling value for OR gate. What is the non-controlling value for OR gate? Please type in the chat box non-controlling value. One is the controlling value. So controlling value means if this value is existing at the gate input, it means irrespective of other inputs, the output is same. Thank you, Sai Kumar. So 0 is the non-controlling value. If it is 0, you are setting B is equal to 0, then whatever A will be having, that is directly going at Z, right? So it means you have to put CC0 of B plus 1 and plus CO of Z. Combinational observability of Z, because you are observing the effect of A at the output, right? Likewise, for B, you will be having CO of B is equal to CO of Z plus CC0 of A plus 1. Likewise, if there are 3 inputs in OR gate also, can you please help me out that what will be the combinational observability for COA? So here in this formula, we will just add CC0 of, because that is the combinational controllability 0, which is the non-controlling value for OR gate. So that's just like this, we will keep on adding the non-controlling combinational controllability values for that particular branch and we'll get the result, right? So likewise, let us come for XOR gate. So for XOR gate, it is a little bit hard to find out the observability. So why it is hard? Because there are certain combinations. For example, I just want to find out what is the input A was. So what I have to fix to input B. So if input B is at 1, right? Let's say input B I have typed to 1. Now, if I am changing its value from 0 to 1, can I observe that? Yes, I can. B is 1, A is, let's say, 0, B is 1, A is, let's say, 1. So what is the output? The output is changing from 1 to 0. It means I can observe. If there is a change, it means I can observe. So I really do not care what is the value of B is, right? Because if B is 1, then the value is changing. Likewise, if B was 0, then the value was changing from 0 to 1. So it means in that case also the value of Z was changing, right? So it means I can observe in both of the cases, whether B was 0 or B was 1. So it means what I have to, how I have to find out observability of A. I am free to choose 0 or 1. I am free to fix 0 or 1 at B, right? So it means I will take minimum either of CC0 or CC1. Minimum of that I will be taking, and then I will be doing plus 1. Why we are going to take plus minimum? Because our level, our job is to keep it minimum possible. From infinity, our job is to bring towards 1 or 0. That is our goal. So that's what we will keep on taking the minimum value if multiple values are the options. Likewise, CO of B is equal to CO of Z plus minimum of CC0 of A, comma CC1 of A plus 1 because of the level change. Why CC0 and minimum we have taken? So the reason is this. We are going to fix A is equal to 0 and we are changing B. So it is going to change the output. We are going to fix, let's say, A is equal to 1. A is equal to 1, we are going to fix, and B we are going to change. So if we are changing, let's say B was X, so I will be having X dash at the output, right? So because of that, we will be having the formula minimum of CC0 of A, comma CC1 of A. Likewise, for NAND gate, See, this was AND gate. This is NAND gate. I want to observe the effect of A at the output in this particular case. How I can observe? The same thing. I'll be observing this effect of this. First of all, I have to make it the non-controlling value. Non-controlling is 1, right? So once the non-controlling value is there, whatever A was there, just inverted of that will appear at the output. Okay. So if this is 1, 1 ended with A and whole dash of that, that is A dash. It means the output bit is going to flip according to the input value of A. It means I can observe it. So you please note it, make a note of it. The observability of the inputs in AND gate and NAND gate is same. The expression for observability for AND gate and NAND gate is same. For controllability, the 0 and 1, because this is flipping the bit, right? So the controllability is the output from 0 to 1 and 1 to 0, that is exchanged. But the observability formula will remain same. Likewise, can I say that for NOR gate also it will remain same? Right? And likewise, can I say that for XNOR gate also it will remain same? And for inverter, whatever the observability of COZ is there plus 1, because there is no other input. You can just observe it directly. So that's how the observability can be calculated. What about the branches? So these are the fanouts. We are observing from here to inside this. So CO of A will be the minimum possible because we are free to observe at any of the outputs. All of the outputs are visible to us, right? So here, since there was no circuit in stem and branches, since there was no circuit, no logical circuit, only a node is there, right? So we will not make plus 1. Plus 1 is not over here. Only minimum of COZ1, COZ2, COZN, like that we will be having, and our job is done. I hope you understood till now. Type Y in the chat box, or if any one of these we need to repeat, please feel free to type repeat. Yes, dear participants, if you understood whatever we have discussed, you may type Y in the chat box. Yeah, so it seems you are tired very much. Okay. Thank you, Prashant. Thank you. Thank you. So let us proceed now. Let us proceed now. So in scope measures, basically, there can be a problem of error due to stamp and reconverging fanouts. So what happens? Scope measures wrongly assume that controlling and observing are actually independent events. In that case, it is going to create the problem. For example, in this particular case, there is a stamp 1, 2, 3. These 3 are there, right? So in this particular case, observing and controlling X, Y, Z, these are actually dependent, and these are depending especially on this input 1. These are dependent. So in these cases, actually there is a correlation between X, Y, Z, all the events. So sometimes it can give you the erroneous output. How it can give? So exact computation of measuring is NP hard problem, and definitely it is impractical. So it is shown over here that how the correct values will be in the scope measure CC0 and CC1. The first two are CCs. First one is CC0, CC1, and then there is observability. How you can measure it? So let us take this in this example. Let us try with our whatever we know. With that knowledge, let us try. So we will start with input 1. Controllability is input 1, 1. So let me take it in this way, CC0, CC1, and I am putting the bracket. So input controllabilities are 1, 1. And by default, all other nodes are infinity. Okay. These are the fanouts. So fanouts, I will be having the same controllability by definition. So this is also 1, 1. Let me put 1, 1 only. And this is also 1, 1. Okay. Now this is 1, 1. This is output. CC0 of this, minimum of CC0, that is 1. CC0 of this is what? For 0, I have minimum of A and B. Minimum of CC0, that is 1 plus 1. CC1 of Z is what? CC0 of A plus CC0 of B, that is 1 plus 1. Plus level change, that is 1. So this becomes 2, 3. 2, 3. And likewise, for this gate also, it becomes 2, 3 because same set of inputs, same set of controllabilities. Now let's come to this. So if we are reaching over here, the controllability will not affect because this is input propagated towards the output. But when we are taking it reverse, then it will create some problem. So look at this, CC0. CC0 is only possible when all the three combinations are set to 0. So 3 combinations set to 0, CC0 of this, CC0 of this, CC0 of this. How much it becomes? 2 plus 1 plus 2, 5. And plus 1 because of level change. So this becomes CC0 of this becomes 6. And then we have to take the minimum CC1. Any one of the input is expected to be 1. That is, we will be taking the easiest possible. Easiest possible means minimum value. So minimum of all these three values is CC1 of this. That is 1. 1 plus 1, that becomes 2. So these are the CC0 and CC1 values of all these gates. So let me take it in this way. Yeah, now it seems to be good. Now we have to calculate CO. We have to calculate CO. So let me change the pen so that we can calculate CO with different pen. So for CO calculation, we will be assuming that the CO for this is 0. Okay. Now we have to backtrack. So backtracking this, if I want to calculate CO of this, how I will be calculating? Non-controlling value at the other inputs. It means I have to put 0 over here, 0 over here. Non-controlling value is 0. So it means CC0. I have to take this plus this. How much it becomes? 1 plus 2, that is 3, plus 1 level change and plus this output. How much it becomes? 4. So CO of this branch becomes 4. Now CO of other branch, whatever CO of this branch is there, the same branch that is similar to it. So this is also coming 4 by the similarity index. Likewise, let us calculate for the middle branch. This is Y. So for Y branch, what I can have? Yes, what I will be getting for the Y branch? First of all, I have to make both of these non-controlling. That is 0. And this is also 0. 2 plus 2, it becomes 4. Right? 2 plus 2, it becomes 4 plus 1 more because we are coming back towards this. So level change. One OR gate is changing. So this becomes 5. 2 plus 2 plus 1 because of level change and plus this 0. Okay. So we are left, we are having 5. Observability of this is 5. Observability of this is 4. Observability of this is 4. Now we have to proceed next. The observability of this I have to identify. So observability of this I can identify in this way. I have to make sure that this is non-controlling. It means it has to be 1. And for 1, we are having CC1 is equal to 1 for this. 1 plus the observability of this node, this particular node, that was 4. This becomes 5 plus 1 more because of the level change. So I am having the value 6 over here. Observability value becomes 6 over here. And because of the similarity, because this input was 1, 1 and this is also 1, 1, so observability of this is also 6. Likewise, let us calculate for this one. Yeah, for this one we have already calculated. It was 5, I guess. It was 5. So the observability for this was 5. Now we are left with this. Let's calculate the observability of this. So we have to put this to 1. controllability of this 1 is 1 plus observability was 4 and 1 is level change, so this becomes 6. Okay, this becomes 6. This upper branch becomes 6, and likewise this branch also becomes 6. Yeah, so it was 4. This was also 4. This was 5 observability. We calculated this as 6, this as 6, and we calculated this as 6, and by default it will also come 6 because 4 is the output observability. Then we have to fix it to 1 and then plus 1. So 4 plus 1 plus 1, you are getting it 6. I'm not able to write it correctly. This is also 6. Now this is the stem. So observability for the stem is minimum of all. So minimum of all, we will be getting it 5. And this is what we will be getting, observability 5. So in this way, we can calculate it. Yes. Okay. So now this was a combination logic example, and let us have a sequential logic example similar to this. So what is the sequential logic example? In sequential logic, definitely you will be having the flip-flop, and then a feedback will be there. The output and input are connected somehow. So this is a sequential circuit. I think we should have a combination logic. Yeah. So first let us have for the combinational logic, and after that we will be having the sequential circuit controllability and observability. So this is the combination logic. This is the combination logic. It is having two inputs. One is R, and then this is another input, and this is primary input. Let's say I7 and I8. These 1, 2, and 3 inputs are there. There are 3 outputs. Okay. Now I have to find out the controllability at each and every node. So before going for the controllability analysis, first of all, for any analysis, first of all, what you have to do? First of all, give the gate numbers. So the gate numbers are given 1, 2, 3, 4, 5, 6, like that gate numbers are given. Now give the level numbers. So these circles are going to show you the level number. So the first level is this. Then this is the second level. This is the third level, and this is the fourth level. So first, second, and third encircled numbers are the level numbers. Then also give the name to each and every branch. For example, you can start with this A, B, C, D. Then these are also the stem is there. So E, F, G, H, I, J, and then this is Z. So let me make it K. Okay. Likewise, give them every line give some number. Every gate give some name and level numbers also. We'll start with the minimum level first of all, because as the level is going to change, level change means what? We have to make +1. Level change means we have to make +1. So it means it is going to create some at least 1 + 1, right? It is going to make it. So first of all, controllability through level 1 we will be checking. So these were the level 1s. So for level 1s, whatever input we have, these are the inverters at level 1. So controllability of CC1 for the inverter is CC1. Let's say this was C branch. This branch is C. So CC1 at branch C can be written as CC0 at the input of the inverter, that is R, right? +1. So CC1 of the inverters was 1 only. So that's what both of these will become 2. Now for level 2, let us check for level 2. So determine for level 2. So for level 2, basically this is AND gate. So for AND gate, controllability for 0 is minimum of both of these. So 2, 2, G at CC0, you have 2, 2. CC0 for both of these is 2, 2, right? CC0 of this is also 2 and CC0 of this is also 2. I'm sorry, there is some issue. Yeah. So for level 2, CC0 of this is 2, 2. This is also 2. So minimum of CC0, that becomes 2 plus 1 level change. So that becomes 3, right? Likewise for CC1, I have to make CC1 plus CC1 of all the inputs plus level change. So that's what it is 5. So 3, 5 I will have. Now this 3, 5 I will have over here. And after that, because there is branching, so at this branch also 3, 5, at this branch also 3, 5, at this branch also it is 3, 5. For all these three, it will be 3, 5. This was 1, 1. So for all these two branches also it is 1, 1 only. Now we have to go for level 3. So for level 3, this is the level 3. This is, let's consider for this first of all. So CC0, you have to take minima of these two. So minima is what? 1 and 3. Out of this, minima is 1 plus 1 more 1. That becomes 2. And for CC1, you have to take 1 plus 5 plus 1. CC1 of A plus CC1 of B plus 1. So this becomes 2, 7. This becomes 2, 7 over here. Since it is 2, 7, so this is also 2, 7, this is also 2, 7. Likewise, let us consider for this. So this is NOR gate, right? So CC0 for NOR gate is what? CC0 for NOR gate. So just consider CC1 for OR gate. So CC1 for OR gate was what? Minimum of CC1. At any one, if CC1 is there, that is going to give you 1 for the OR gate and 0 for the NOR gate. So take this one or this one, that is going to give you 1 plus 1. You understood? For OR gate, whatever we had for CC1 at the output, that will play for CC0 for NOR gate. So minima of CC1 at any of the input plus 1, comma, CC1 for NOR gate is equivalent to CC0 for OR gate. CC0 for OR gate is difficult most, or CC1 for NOR gate is difficult most, means all of the inputs are expected to be 0. So this is 3 plus 1 plus 1. That becomes 3 plus 1 plus 1 and plus 1 more 1 because of level change. So 5 plus 1. So this becomes 2, 6. So we have 2, 7 over here and this becomes 2, 6. So now we have the OR gate as the last stage. So OR gate as the last stage, we can have, this is the OR gate as the last stage. What we can have, for 0, I have to make CC0, I have to make CC0 of A plus CC0 of B plus 1. That becomes 2 plus 2 plus 1, that is 5, comma, for CC1. For CC1, I will be having minima of these two. So 6 is minimum, right? Plus 1 because of the level change. There is a level change. So this becomes 5, 7. 6 plus 1 becomes 7. And we are now happy with all the numbers because now there is no infinity. Initially, we will only consider these inputs as 1, 1. And all others we will set to infinity. Initially, we will do it like that. And after that, computing all the level 1 to level n will reach to some non-infinity value. It means now we have calculated the controllability for all the branches, right? Now we have to find out the observability. So we will check for the first level, second level, third level, like that we will go. Observability, we will start from the output. We'll assume that the output is having the observability 0. So the output observability, there are 3 outputs. We will assume that output observability is 0 for each and every output. Then the level is changing towards reverse direction. So the level 1 is this, then the level 2 is this, level 3 it is this, and this is the last level 4, right? So now let us calculate for the level 1. So outputs are having CC0, this single letter bold one is the CO, and this is on one of the corner. You will type that how you are going to consider the brackets, or maybe you can take a square bracket, or you can take all these things in one bracket also. CC0 comma CC1, this is the way how it is expressed in this way, and CO separately just beside to that, it is expressed in this way. Square box is expressed for the observability levels, and circular box numbers were expressed for the controllability analysis level numbers. So controllability, we are going to control from the input towards the output. That's what the controllability started from 1 to n towards the output. While in the observability, we are trying the observability from output to input. That's what the observability level from output, it is set to 1, to the input it is the highest level. Okay, now let's consider the observability. First of all, let us consider for the level 1. So this is the gate level 1. So this output observability is 0. Okay, now I have to, let's say, calculate for this. So I have to make sure that the other one is the non-controlling. So what is the non-controlling value for OR gate? Just type in the chat box non-controlling value for the OR gate. OR gate non-controlling value. What value I can put at the branch of this OR gate so that output is not changing because of that. So that is 0, right? Thank you, Sai Kumar. So 0 is the non-controlling value, right? Thank you, Prashant. Thank you. So here CC0 is what? 2 plus 1 because of the level change, and plus this is already 0. So I will be having 3 as the observability of this branch. I can put it here, 3. Likewise, because this is 2, so vice versa, if I'll be calculating, there is no need to calculate. I'll find that 3 only. So that is 3 and 3. Now let's come to the next level. So next level is this second level. So first let us calculate for this one. So the observability of this is 0, and for this it is 3. So in this tab, observing from 2 of the fan outs, if I want to take it for this time, I will be taking the minimum one. So I will be taking the 0 is the observability of this. Now I have to find out the observability of this branch. How I can find out? This is 0. I have to make sure I have to tie it to 1, and then plus 1. So this tying this to 1 is 5 plus 1 more, that is 6. So observability of this is 6, and vice versa. Tying this to 1 is 1 plus 1. So the observability of this becomes 2. This becomes 2, right? The observability of this becomes 2. But the observability of this is what? 0. So 0, 2, and whatever I will be calculating over here, that will be definitely more than 0, because there is one level here and one level here. So it is definitely more than 2, right? So I am skipping that, and I am finding out that the observability of this is 0, because minima of this, and this fan out branch, I will be having the observability of gate number 3 and gate. So I will be having observability over here, that is 0, right? Observability at this node will become 0. Now let us calculate for this gate. So calculating for this gate, what you have to do? Just take the observability, that was 3 for this, and since this is NOR gate, but the non-controlling values for the NOR gate also are the same, 0. So this 0, this 0. Just add both of these, 1 plus 3, plus the observability plus one more one. How much it becomes? 1 CC0 of A, CC0 of B, and CO of the output, and plus 1 level change. So this becomes what? 8. So for this, it becomes 8. Okay. Likewise, for this also, because this is the same, right? Inputs of this and this were same. So for this also, this becomes 8. Now we have to calculate for this. So for this, let us calculate. So it is CC0 here, CC0 here. 1 plus 1 and 3 is CO, 5. 1 plus 1 plus CO plus 1 level change. How much it is? 6. So this becomes 6. So we have already discussed it was 2, it is 6, and this was 0. So over here we will be having it 0. Okay. So now we are coming to the level number 3. So here we have 0, and then we are going to calculate the CO of this. How I can calculate the CO of this? So CO of the output plus 1 because of the level change plus CC1 of this. So CC1 of this is what? 2. So that becomes 3. So this is 3. And by the similarity, because 2 are here, 2 are here. So without calculating, you can just write that this will also become 3. So this becomes 3, 3. Now this is the last level, but not least, of course, CO plus 1. These are the inverters. So you just need to put CO plus 1. So you'll get 4, 4. Here also 4, here also 4. Now this is the fan out branch. So here it was 8 and here it is 6. So what will be the observability? This is 4. In this manner, we can calculate all the controllabilities and observabilities of a combinational circuit. If you have any question so far, please ask related to this combinational controllability and observability. If you do not have any question, type N in the chat box. So far, if you have any question, please feel free to type in the chat box. If you do not have, please type N in the chat box. Thanks, Neha Singh, Prashant. Okay, so shall we proceed? You may type Y in the chat box. Okay, so now the combinational controllability and observability are actually very simple to find out. Let us come to the sequential measures. So what's the difference between sequential measures? Combinational increments in CC0, CC1, COs we will be having whenever we have a pass through a gate, either forward or backward. Forward we will be having when we are calculating COs. Backward we will be having when we are calculating COs. Okay, because observability backtraces and controllabilities propagate forward. Likewise, in the sequential, the increments in sequential controllability 0 or the controllability 1 is going to happen in the forward way, and SO it is going to happen in the backward way only if a pass is through a flip-flop or the memory element. Please make a note of it. In this, it is a gate is actually passed by. In this case, flip-flop is passed by, then only there is the increment, otherwise there is no increment. Okay. So for any calculation, unless until we are not getting the final result, all the branches are not infinity, by that time we'll keep on calculating both the combination and the sequential controllabilities and observability. Okay. So yeah, we are going to cover it. Maybe we can take a little bit more time than 1 p.m. So please bear with me, maybe for next more 10 minutes after 1 p.m. So for D flip-flop, let us have the equations first understand, because combinational controllability, we have done the example, we understood that well. For D flip-flop, we have to repeat the same thing again. And here also the concept is same. Controllability means how it can control. Observability means how I can observe, right? So let us calculate CC1 of Q. Here CC1 or CC0 of all these three. These three are the inputs. For the CC0 and 1 for these are easy. We will be getting from somewhere. If these are the primary inputs, then we will set all of these to 1, 1, 1. Like that. We are going to do that. Please wait a minute. Hello. Yeah, so I'm sorry. Uh, Here, please observe CC1 and SC1, CC0 and SC0. The formulas are same except one thing. What is that one thing? There is the increment. There is the increment by 1 in case of SC, while there is no increment because the pass was a flip-flop. Flip-flop is not a combinational circuit. That's why the formula will remain same in each and every case, whether it is combinational or sequential. Combinational means all the things related to combinations you have to apply in the formula, but plus 1 only when this is the corresponding circuit. If it is a combinational circuit, you have to do plus 1 in the combinational controllabilities. If it is a sequential circuit, you have to make plus 1 in the sequential circuit. So since it is a sequential circuit, so all the combinational data is not made plus 1, but the sequential controllabilities are made plus 1. That is the take on this. So here, let us find out the formula. There is only single output Q. If Q bar was also going to exist, then Q and Q bar are just reverse. So SC0 and SC1 of Q and Q bar will actually get interchanged just like AND gate and NAND gate. I hope you got my point, right? So let us consider this CC1 of Q. CC1 of Q, how I can determine? CC1 controlling the output of this D flip-flop to 1. My job is to control this to 1. How I can control this to 1? What are the ways? Controlling the output of this flip-flop to 1. What are the ways to control it? So I am presuming that this is going to take the reset in its primary mode. 1 means it is going to reset. 1 means the output is going to become 0. And whenever circuit is working correctly, it means I have to put reset to 0, right? So this circuit becomes active if I am going to make reset is equal to 0. By default, reset is 0. So first of all, I'll take reset CC0 of the reset. In default mode, the reset is 0. So I'll make it CC0 of reset. Plus, I want to make Q is equal to 1. So I have to make sure that D input was 1. The input data at D was 1. Okay. So it means CC1 at D. Plus, what about clock? So this is the level, ACE triggering. So if it would have been the level triggering, let's say directly clock was given. In that case, I was happy with CC1 of C. But for the level trigger, you will be taking both CC0 and CC1 because it is changing from 0 to 1 or 1 to 0 in either case. So it means you have to take that into consideration. Okay. So you have to make sure for all the A's triggering, you have to make it CC1 of C or CC1 of 0 of C. That you have to take for A's triggering, whether it is positive A's triggered or negative A's triggered. Because in both of the cases, either you are switching from 0 to 1 or you are switching from 1 to 0. So anyway, CC0 and CC1 in both of the cases is counted, right? So that's what we have taken this for the is triggering. CC1 at D, because that is responsible to make Q is equal to 1. Reset we have to deactivate. Deactivating reset is CC0. So that's what CC1 of Q is given by this formula. Same formula is applicable for SC1 of Q, and this is +1 because there is a level change of the flip-flop. That's what +1. Now let us calculate CC0. So for CC0, if I am making reset is equal to 1, then reset is going to make my output 0, right? If this is 1, irrespective of what it was, my output is 0. Or in other case, so it means there are two combinations. So first combination or second combination. So it means I am happy to choose minimum of these. Okay. So minimum of these is what? So I will be taking minimum of CC1 reset. Okay. CC1 reset, comma, CC1 reset and the active age of the clock. So it is up to you what type of flip-flop you are using. In this particular case, the flip-flop used is saying that there is a level, there is active age of the clock, and you are going to apply reset is equal to 1, then the output is going to change. Okay, that's what it's been taken in this way. If reset is not synchronized with the active age of the clock, you can directly take CC1 of reset, comma, CC1 of 0, and then the clock change. Okay, and then whatever it was. So this is the formula, you can have it. Yeah, okay. And this is analogous to your sequential formula. And now we will be having the CO formula. CO and SO formula. Observing the inputs. Observability of Q is actually the easiest possible. And then we have to backtrack. Backtracking means level change is there for the sequential. So for sequential, we have to add 1. All the sequentials plus 1 we will be doing. SC, SC, SC like that, and +1. So let's calculate CO of D, how it is calculated, so that we can come to the point how SO of D can be calculated. So in order to find out the effect of this on the output, what I need to make sure? I have to make sure that this is not active. It means I have to make reset is equal to 0. I have to make active age of this clock. It means CC0 of C plus CC1 of C and the CO of Q. These are the things I have to take into consideration. So CO of Q plus active age of the clock plus deactivating the reset. That is going to give me whatever at D input I will be having, the same thing I will be having at the output. Okay. So in this formula, basically along with this, you have to add one more thing I forgot. It is CC0 of reset, because once you have deactivated that, then only this is going to work. So this is comma, and then with this you will be having this also plus this also. Okay, so it means it is CO of Q plus active age of the clock plus deactivating your reset. That is your CO of D. Likewise, if you want to check what was the reset, so CO of reset, how you can check it? So CO of Q you can have. You can only visualize the reset if previously it was CC1 at Q was there. CC1 was there, then it will change to 0, because reset, what reset output gives? It gives 0 output. So it means previously it was 1, then only you can see that it is 0, right? If already it was 0, you cannot visualize. So that's what CO of Q plus CC1 of Q, mandatory you have to add, plus CC1 of reset. When you can see the reset, whenever you are making it CC1 of the reset, then only you can check it. And plus, because we have taken the reset in sync with the clock, so this is for the active age of the clock. Okay. Now, what about the clock? And the analogous formula we will be having for the sequential observability. So CC, CO of combinational observability for clock. How you can have it? So CO of C, you can have minimum of you can see there are three things. First thing is going to cover CO of Q plus CC1 of Q plus CC0 of D plus active A's. You got my point? So it means you have to make the active A's of the clock, plus you have to make sure that the D is at 0 and Q is at 1, because D is going to change. If it is 0, then Q will get changed from 1 to 0, right? That's what it's been taken. The active A's along with the different input and output. This combination has been taken. Next combination, in all these combination, of course, COQ is common. You can visualize over here, COQ is common in all of these. So next one, with the help of reset active also, you can see that, right? So reset active, CC1 is there, and then you are going to make reset active. So since active age of the clock is there, so it means the effect of Q is also visualized. And last but not least, reset is not active. Then with the help of CC1 at D and CC0 at Q also you can visualize. Okay. So these are the formula, minimum of these, because these are the three combinations. With the help of that, you can make the changes on Q with the help of clock. That's what minimum of these three is taken. So testability computation, how it is computed, let us have a look at that. So this is the circuit example. This is the combinational circuit only, but in a modified way. So it has a feedback also, right? So we'll do the same thing. First of all, give the name to all the gates. Give the level. These are the levels. Give the name to all the gates. 1, 2, 3. Name, number, or whatever. There are flip-flops also, so give some number to them also. And the level is for the flip-flops also. So this level is changing over here. So this is the 5th level. Okay. Now in this, there are two inputs. One is this input and another one is the clock input, right? So here it's been taken in this way: CC0, CC1, then SC0, SC1. This is taken in the small bracket and this is taken in the bigger bracket. So this is the denotation. So whatever denotation you are using, you write that maybe left topmost or the right topmost corner of your solution, right? So the first, this is the combinational controllability and this is the sequential controllability. So the thing is, sequential controllabilities will always start with 0. Combinational controllabilities, easiest level, we are going to start with 1. And sequential controllabilities, we are going to start with 0, right? Because input, it means we have not invoked anything, right? Easiest level, we will be taking that 0. By default value for sequential controllabilities, we will be taking 0. Unless until it is not told that this particular value you have to take. Okay. So these are the inputs. These are the stamp branches. So we have taken that. Now crossing this. This is the inverter, right? So inverter combinational controllability is +1. So it will give you 2 + 2. We have already computed that. So I'm not going to compute that again. So this was 2, 2. Let me make it here. But here, this in the previous case, it was the input. But now it is a feedback. It is a feedback. So if this is a feedback, it means what? I have to make sure that this is infinity, infinity. It is not 1, 1 or 0, 0. It is infinity, infinity. Here I am getting it 2, 2. These are 2, 2. So now for AND gate, I can calculate. How I will calculate? This is first iteration. So now I am here. Both of these are 0, 0. The reason being, when I am crossing this inverter, so I'll be using the sequential controllability of 0 is equal to of output. Let's say output is A of the inverter. So sequential controllability of 1 at the input. Let's say input is R and nothing plus. So that was 0 only, right? Because inverter is a logic gate. It is not a flip-flop. So that's what SC0 of A is equal to SC1 of R. So that's what these are interchanged, but this will remain same. Now for this, I want to calculate. How I can calculate for this? So in order to calculate for this, I have to use the formula. Which formula I can use? One formula was for CC0. CC0 says that CC0 of the output is minimum of CC0 plus 1 for the combination, and for sequential it is minimum, right? So minimum of CC1, out of this, these are infinity, this is 2 and 0 combination. So 2 plus 1 is 3 and this remains 0. Minimum of CC0 is 0 and sequential there is no plus. And this was actually infinity only. Why? Because here there is the addition of CC1s. So CC1s, these are added with something. So it will remain infinity. I hope you got it. So we'll get this on this stem. And from this stem, it is propagating to all these three. At this and this place, it is going to propagate. Okay. Now let's go further. Go to the level, next level. Once we have computed that, so we can visualize that this is going to give me 3 comma infinity. Let me take it here, 3 comma infinity and 0 comma infinity. So and what about this? These are actually, look at this, these are coming from here, so these are infinity, these values, right? These are infinity. So can I compute for NOR gate? So for NOR gate, how I can compute? NOR gate means just inverse of OR gate. So for OR gate, I have CC0 is the hardest possible, means sum of all. So it means CC1 of this will be the hardest possible. So I can compute CC0. So CC0 for NOR gate is the minima possible. What it will come? CC1, right? Minima possible CC1. So CC1 minima possible is what? 1 over here. Others are CC1 infinity over here, infinity over here. So it means minima of CC1 plus one more one level change. So this is going to become 2. Another one is 0, right? Another one remains 0. And the hardest level is infinity because there the sum is required. So that becomes infinity only. Here you can visualize one thing, that the SC of all these, unless until they have been passed through a flip-flop, they are 0. Till here, all the SCs are 0. You can visualize. All the SCs are 0 till here, unless until they have been passed through a flip-flop. So now let's compute to the next. So now we are here. Yeah. So first we have to compute for this also. So for this, in order to compute for this, look at this. There are one, it is coming from here, and this is coming back from the output, so that is infinity. So we are surviving on this only. So it means we can calculate the whatever we can have for minima. So we can calculate CC0. CC0 will be CC0 of this plus 1. That is 4 comma infinity and 0 comma infinity. So now whatever we have over here, that is there at the output, that is there at this input also, right? So let us calculate for the next one. Next one is the NOR gate. If I have both of the inputs, yeah, both of the inputs of CC0 are available. So it means I can calculate the CC0 for OR gate. CC0 for OR gate is the sum of CC0 of this, CC0 of this. So I have CC0 of this, that is this one plus this one. 4 plus 2 is 6 plus 1 more because of level change. So this becomes 7 comma infinity and 0 comma infinity. So I'm having here 7 comma infinity, 0 comma infinity at the input of D flip-flop. At the input of the other D flip-flop, I'm having 3 comma infinity, 0 comma infinity. The clock input is 1, 1 and 0, 0. That is definite, right? Reset is not existing. Clock is positively edge trigger. Edge trigger means CC0 and CC1 of clock. Both of these will be added as and when it is required. Okay. So now let us calculate for Q1 and Q2. So for Q1 and Q2, if I want to calculate, I will be proceeding for the level 5. Level 5. Q1, how I can calculate for Q1? CC1 of Q1. When the value of when the value of Q can be 1. So it requires, first of all, D is expected to be 1. That I cannot calculate because it is infinity, right? So it means this is expected to be infinity. What about CC0? So I can calculate CC0 of Q with the help of CC0 of D that is available with us. Okay. So CC0 of D and plus active edge of the clock. Active edge of the clock in combination it is 1 1. So it means 1 plus 1. And there is no gate level, so that's what we will not do anything. So how much we will be getting? CC0 of D, that is 7 in this case and 3 in this case. So 7 plus 2, that becomes 9 over here, and this becomes this was 3 plus 2, that becomes 5 over here. What about the sequential? So for sequential, all others were 0, so this is set to 1 and this is set to 1. You got my point? Because this was 0 and these were also 0 for the sequential, right? So 9 1 and 5 1, comma infinity infinity, this is what we have. Okay, once we have these values, then we can back propagate. Yeah, let's start the next iteration. If we have these values, we can start the next iteration. So for next iteration, how we can proceed? We have the value over here is 5 comma infinity and 1 comma infinity. This is inverter. So inverter means we are flipping. So the 0 is affecting the output controllabilities of 1. So this becomes 5 plus 1, that is 6. And SC0 is responsible for SC1 of the output. So that's what we are having 6 1. Now we can calculate actually CC1 for this. Look at this. Minimum of CC0 or SC0 has not changed. So it means whatever calculation was done in the previous iteration, that has not been changed. But we can update the CC1 and SC1. How we can update? For CC1 and SC1, we have to add. CC1 means this 2 has to be added with 6. CC1 of A plus CC1 of B plus 1. So that's going to give me 2 plus 6 plus 1, that is 9. Okay. Likewise, 0 plus 1, that is going to give me 1. Likewise, we can calculate this for this one, and whatever we have for this one, that is applicable to this one also and this one also. So these values were infinity, if you remember. So these values, CC1s of NOR gate. CC1 we can have only if I have CC0s of 4, right? CC1 for OR gate is having CC0 of OR gate is having CC1. Yeah, wait a minute. This is CC0 was already calculated. I believe it was already calculated. Yes, it was calculated. So CC1 of this is equivalent to CC0, sum of CC0s for all. Okay, sum of CC0s for all. So now what is the updated value? So the updated value which was infinity over here, that has been updated. That has been updated to 9 to 1. So just add these values, 9 1 and this is 1 0, and from it here it is 3 0. So 9 plus 1 10 plus 3 plus 1 14, and 0 plus 1 plus 1, that is 1. So that's what it becomes 14 1. Okay, I hope you got it. So it means we have calculated this in the second iteration. This is value is also fixed. It means these values are fixed. These values we have calculated. Now let us proceed. So from this we can proceed now further, and we can proceed here also. So if we want to proceed over here, we can calculate. Look at this. CC0 we calculated earlier, right? CC0 for 0 we calculated earlier, but still I cannot calculate CC1 because still it is infinity. So this will remain infinity only. Okay, now let's try for this. So I have calculated CC1 for this, and yeah, other portion CC1 is infinity, but for CC1 for OR gate, I just need minimum. Either A is 1 or B is 1. That is going to give me 1 anyway. So we will be having this plus 1. 14 plus 1, 15, and 1 plus 0, because sequential controllability, we will not increase 1, right? So this is 7 comma 15 and 0 comma 1. So the previous values are same, only infinity values are updated if you look at closely. Okay, so now we have calculated this also. We can proceed further and we can calculate the Q1 and Q2 now. So how we will be calculating Q1? The same formula. So for Q1, CC1 we want to calculate, we can calculate. All the values of D are available, all the values of CL are available. So CC1 of Q I can calculate. Q1, let's say Q1. That is CC1 of D and plus CC1 and CC0 of clock, that is 1 plus 1, 2. Okay, CC1 of D is what? This is 15 and this is 1. So 15 plus 2, 1 plus 1 because of level change, and clock 0 plus 0. So this becomes 17 and this becomes 2. So here this becomes 17 and this becomes 2. Likewise, you can calculate for Q2 also. So for Q2, how you will be calculating? So these are the values, plus you have to add these two and plus these two. So 9 plus 2, that is 11, and 1 plus 1, that is 2. So these are the values. So now after these iterations, now you can visualize that every branch is having a definite number, right? Every branch is having a definite number. So now you can see that yes, the controllability and observability, controllabilities for each and every branch have been computed. Once the controllabilities are computed, we can go for the observability. How we can go for the observability? So observability, we will set over here 0. There is only one output, Z. So we will set the observability of this at 0, and for all other rest of these, we will set it to infinity. So if this one is 0, look at this. There was the stamp that was infinity. We have to take for the stamp minimum possible. So observability of this is also 0. If the observability of this is 0, can I calculate for this? Yes, I can calculate. I have to make CC1 of this plus CO plus 1. So the observability of this branch becomes 10. And since it was 1 and level change doesn't really matter, so this becomes 1. You got my point? Likewise, observability for this branch. Look at the controllabilities of this. So controllabilities were 17, 2, right? Add the observability plus 1, that is 18. So the observability for this branch becomes 18, 2, right? Yeah. So likewise, you will keep on calculating the observabilities, and finally you will be finding the observability in this way, whatever are listed in this. If you want, I can explain this. The formula is same. You'll keep on calculating the observabilities. First you have calculated for this. So you found 18, 2, and this was found, where is this value? 10, 2, I believe. It was 10, 10, 1. Yeah, it was 10, 1. So this 10, 1. Just update these and then keep going on backward. Observability will be taking from forward to backward side. If there is again next iteration is there, then that will keep going on. So if you are here, then from here you are going back over here. Here you are going. So if you are here, the observability of this is set to 10, 1. Now you can calculate the observability of this. Can you calculate this? Yes. How you can calculate the observability of D? D is 0 or 1. How you can find out? So observability of the output plus CC1 plus CC0 and plus level change if needed. So this becomes 10 plus 2, 12. And for sequential, it becomes 1 plus 0 plus 0 and plus level change. So this becomes 12, 2. Okay. Likewise, if you know this, it means you can check the observability over here and here. So check the observability because 12, 2 is known to you now. So if you know 12, 2, You will come back. So non-controlling value of this means 0. You have to select this one. Add these values. So this becomes +3 and here +0. Level change because it is a gate, so it is +1. So 12 plus 3 plus 1, that is, it must be 16. 15. Yeah, it is 15. So it is, no, something else I've taken, right? This value was having these values. So this is 4 plus 1, that is 17. And this value will remain 2 plus 0, that is 2. So this becomes 17, 2. Then you will proceed further and likewise you will be calculating. Now you are here and likewise calculate for this. Calculating for this becomes add 2 plus 1, that is 15, and there is no add in this. Okay, so this branch becomes 15 2, but this is not taken into consideration because this was 0 0. So of course this is going to be 0 0. There is no need to even calculate for this. Now proceed further. Proceeding further means let us calculate observability of this branch. So observability of this branch means other branches I have to set to 0. 0 means I have to take controllability of zeros of this and controllabilities of zeros of this. So look at this. This is 3 plus 9 and plus 17. This is 29 plus level change 1. That becomes 30. And likewise, this is 1 plus 2. That becomes 3. So for this branch, I have 30 and 3. Likewise, I will be calculating for the next branch. That is this one. So this becomes, again, controllabilities you will be having CO, this plus this, that is 26 plus this one, CC0. Okay, so this becomes 20 and plus level change. So this becomes 28. And likewise, 2 plus this is 2 and plus 1 from here. So that becomes 3. So likewise, you will be calculating and then you are reaching over here. So here you will be taking the minima possible. So see, we have not calculated for this. Right now, we have not calculated for this. So through this, you will be calculating and you will be finding that the minima becomes 18.2. So this 18.2, when you are back propagating, updating it, CC1 you have to add. So CC1 of this is this 6.1. 18 plus 6, that is 24 plus 1, 25. And 18 plus 2 of this plus 1 more, that is 21. So you are getting these observabilities at the inputs of this gate. Reversing this for the inverter, just add 1 in this. So 26, and this sequential will remain same. And likewise at the input you can have 26 and 3. Here at the input of this you can have 22 and 2. So whatever you have over here, just reach over here 22 and 2. From here you can backtrack and you will be getting over here. Observability of D means you have to add CC0 of clock and CC1 of clock and the level change in this case. So that becomes 24 and 3. So in this way, you can calculate all the observabilities of this circuit in one go. So since there is dependence, so randomly you cannot calculate. You have to take into consideration how to proceed. So already we are running behind 14 minutes. So let us conclude the session. And if you have any questions, please feel free to ask. Do you have any questions? If you have any questions, please feel free to ask. If you don't have any question, you may type N in the chat box to show that it is no questions. N in the chat box you may type if you don't have any question. Thanks, Narpendra. Thank you, Suman. Thank you. Voice not receiving. Was it the case? So, yeah, now we have completed the scope analysis. This analysis is really very important, and this analysis give us how hard a circuit can be to observe, to control, and this hardness actually tells us about how the testing can be difficult for us. Okay, so these testing measures we have completed. Thanks, Tejpal. So we have completed the testability measures with the help of the scope analysis. I will be sharing these slides. So please go through these slides. These slides I have taken from a book, that is Agarwal and Brussels. So you may use these slides. I am sharing the PPT only as and when required in your classes, or maybe for the learning purpose. If you have any question in this, maybe tomorrow we can take that question. If you do not have any question now, maybe tomorrow we can have that question. Another thing, I have an announcement that tomorrow evening we will have a quiz. The first quiz will be floated tomorrow evening at 8 p.m. or afterward, that will be published. So you are expected to complete the quiz by Friday evening 6 p.m. Friday evening 6 p.m. On the quiz there will be a timer. We are planning 30 questions, 30 minutes, but whatever the set of questions and the time will be there, you have to take that into consideration. So that we have to make sure that the time is running. So if you are not submitting the quiz on time, it will get submitted automatically if time is complete. Okay, so thank you so much for listening carefully and participating actively. Let us meet 6 p.m. Today evening to have a lecture from Professor C.P. Ravi Kumar sir. Thank you so much. Have a nice day. Thank you.